So hey guys, in this video we're going to take a look at decorators in Python. We're going to look at what they are, how they work, and when you should use them. So before just diving in, we're going to motivate when you might want to use a decorator, how to identify when it's going to be the right tool for you. So if you're just interested in seeing a decorator in action and seeing how to actually implement it in Python, skip to this timestamp. All right, so first, let's consider what exactly a decorator is. So it's going to decorate a function. It's sort of like when you decorate your house for the holidays, right? Whatever holiday it may be, Christmas, Halloween, Valentine's Day, whatever. So your house exists. It's got all of its rooms, all of its furniture, all that's unchanging for the most part. And the decorator just says, let's add a little bit something extra to it. You add the decorations to your house. It's a little bit of extra functionality on top of what's already there. So before we can actually add any decorators, first we have to build that foundation. We have to build our house. So we can use really any function that we want because decorators decorate functions. And what I was thinking, we can just do the classic Fibonacci. So I'm going to do it recursively, so we'll call it recurfib, so I don't want to type out recursive every time. And what this will do is it will return the nth Fibonacci number. So if you'll recall, well, we're doing this recursively, so first you need your base case, and then you're going to have the recursive step. All right, and that might be a separate video. We can talk about recursion, but just bear with me. So we need the base case. So if n is either 0 or 1, that's the first and the second Fibonacci number. So I'm just going to do it like this. It's shorter to write it this way than it would be to write n equals 0 or n equal 1. Just if n is in 0 or 1. And notice this is a tuple because tuples are immutable. You could use a list if you wanted, but might as well use the tuple. Okay, anyway. So we'll return n. So if you want the 0th Fibonacci number, that's 0, you get 0 back. You want the first Fibonacci number, that's 1, you get 1 back. All right, otherwise, so we can put our else here, we don't have to because the return automatically takes us out of the function. So I'm just going to say otherwise, you're going to return the recurfib. And remember the Fibonacci numbers, each one is the sum of the two before it. So we want recurfib n minus 1 plus recurfib n minus 2. And let's just test to see that that works. I'm going to give it an n, or n in range. Let's just print the first 10. See how that goes. All right, that looks good. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2, 3, 5, 3, 5, 8. Okay, yeah, we got them. So there we go. But there's more than one way that you could do this. So let's also do an iterative version of the Fibonacci, just so we have two functions to play with. So you could have two houses on the same block in the same neighborhood, and you're going to put decorations on both these houses. So we'll see what the decorations look like on each one or something like that, okay? So we're going to have two functions. And if you didn't know everything that you can do iteratively, you can also do recursively and vice versa. So it might be more difficult to do it in one or the other, but the two things are equivalent. That's like the Church-Turing thesis, so they're the same. They're reconcilable. So we can also write Fibonacci as an iterative version. And to do that, we're just going to say, hey, the first Fibonacci number is going to be 0. Second Fibonacci number is going to be 1. And then we're going to iterate for x in range n. So we'll get the nth one. Let's say, save the f and attempt because we're going to do a swap. F1 will then equal F2, and F2 will equal F1 plus F2. And then at the end of that, we want to return F1. I think that's right. Let's print it out just to check it. What we'll do is we'll provide two arguments to print. So recursive and iterative. Alrighty. Oops. Oh, I don't know how I did that. Somehow this indentation's gotten off. There we go. All right. If you want to do the indentation like that, the shortcut is Control square brackets on Windows. Alrighty. Ooh, no, we've done something horribly wrong. Let's see. Oh, I reset this here, right? So F1 is F2, so we just doubled it. We needed to use temp here. All right, there we go. Another way we could do this that might be cleaner. This is the typical like swap pattern you'll see in different programming languages. But in Python, we can just reset them like this. So let's say that F1 is going to equal F2, and that F2 is now going to be F1 plus F2. And I think that should be equivalent. We can just comment this out. Yeah. So in Python, that's a one-liner. Okay. So now we have two Fibonacci functions. One's recursive and one's iterative. And you're probably saying, oh, well, all right, that's all well and good. What's that got to do with decorators? I feel like this is a pretty long detour. And kind of right, you're not wrong. But let's look at a question now. So we got both of these. Which one's better? Which one's faster? So, you know, if we actually really cared, we could do some analysis. We could figure out like the big L of these things. But let's just say you're in a hurry. You just want to pick the faster one. So you want to time them. You want to see which one's faster specifically on your machine. So let's import the time module. And we don't want to print all the Fibonacci numbers anymore. So if you don't know how to use the time module, you can get the current time from the computer just like this, time.time. So when it runs, that's going to be the current time when it executes that step. So what we'll do is we'll get the time. We'll do our recursive call. So we'll do recurfib. Then we'll get the time after it's been done. And then we know that the time that it took to do the function is going to be T2 minus T1. So we can print that out. So we'll print out F, and then we're going to print T2 minus T1. So let's make this a little prettier. Fib number. And a new line in here. Time to execute. So remember, you can give print as many arguments as you want, just separated by commas. Save it, let's run it. Oh, we didn't define that. Which Fibonacci number do we want? I don't know, we want the 8th one. Okay, so the 8th one is 21, and it basically happened instantaneously. It didn't cost us anything. So the time, according to Python, was so small that it's just rounded it to 0. So if we want to see something happen, let's maybe pick 15. Let's get it a little bigger. Okay, there we go. So if you want the 20th one, now we're starting to see it's taking time. And this is in seconds, I believe. Okay, So you could format that a little bit better if you wanted to, but that's not the point of this video. Alrighty, so now we know how long it takes to find the 20th Fibonacci number using the recursive method, but what about the iterative method? Well, we got to copy and paste all this stuff. Ready? There we go. Let's see what that looks like. So here it looks like the iterative one's faster. We can make this a little bit bigger, see if that continues. Yeah, the iterative one's going to be faster. And I'll leave that as an exercise up to you to figure out why. We're more concerned about how we can make this better, because that's a lot of copied code, and we had to get the time before, the time after, we had to print it out. That would be pretty annoying, right? It's annoying to write all that out. What if we could make a function that could do a little bit of this for us? So why don't we try to do that? Make a function. Let's call it time it. So that's what we're doing, we're timing. And time it is going to take a function, because you can pass functions as arguments in Python. They're first class objects. So it's going to take a function, and we know that our function takes an argument n. So let's just go ahead and give it an n. So this is going to be the Fibonacci that we're using, and that's going to be the n that we want. So what's time it going to do? Well, time it's going to get time. It's going to run whatever Fibonacci you gave it. Let's say we save that as fib. Then it's going to get the time. Oops. Going to get the time again. And then it's going to print this thing. No need to type all that again. And that's going to be fib. And lastly, we want it to behave the same way. So it's going to return fib back to the caller. So you give it a function, a first class object, and you give it the n. It runs whatever Fibonacci function you gave it with n as the argument, and it times it. So let's get rid of all this stuff. We don't need it anymore. And we're going to call time it. Alrighty, so there it is. Looks like it worked. And you'll notice that every time you run it, you're going to get different times. That's because different processes are running on the machine. There's different things going on. So it's not always going to be the exact same. And that's why using something like big O notation is a better metric for determining which of these functions is better. But anyway, so this worked. This did what we wanted it to do. So this is not a decorator, though. This is just a function that takes another function as an argument. Maybe we can call it like a proto-decorator, but it itself is not a decorator. So now, hopefully you see the problem that we're trying to solve. We want to be able to decorate our function with these time collectors, right? We want to be able, this timer is going to be the whole thing. We want to be able to decorate it with a time it, so that whatever function that we have, whether it be recurfib or iterative fib, we can just apply a decorator to it and it will time it for us. Just sort of what this did, but it's a little bit of a hard-coded solution, and we had to write all this up. You'd have to do this for every different type of function you had. So let's actually go and make a decorator. We're going to call it time it. And just like here, time it is going to take, oops, it's going to take a function. A function is a first class object. I'm going to keep saying that. It's going to take a function as its one and only parameter. Ready? Now, inside of here, we're going to make another function. There's going to be a nested function. Let's call it inner function. Let's call it inner. And this inner function is going to actually do what this time it down here was doing. So we're going to do our time, t1 equals time dot time. Just go ahead and do this. I don't know why I keep wanting to do that. Time dot time. And then we're going to grab this print statement, because I'm not going to type it again. It's actually basically the exact same thing. I'm just going to take all the pieces away from it. All right, there we go. So we got a function inner that is created when we called the function timeIt. So the f no longer is passed as a parameter here. Instead, it's passed as a parameter here. So if you remember your scope rules, this function here, this nested function, can see all the parameters and all the variables that are made inside of the scope or passed into the scope. So there's the function. And then the big function, timeIt function, is going to return this function. So not only can you pass a function into a function can also return a function. So we've basically made a factory that builds a new function, but the new function is just our old function with stuff wrapped around it. It's been decorated. It's been decorated by the timer. Now notice there's one thing that we're missing here. So our function needs this parameter n. So this inner function, which is getting returned, also needs the parameter n. So let's see if we can get that to work. We no longer use timeIt like that. Instead, we can call our function just like normal. Notice there's no print statements down here. So how do you actually decorate your function once you've made your decorator? It's as easy as just using the @ sign and then the name of that decorator. So we're decorating it with timeIt. And then for any call of it, it's going to get applied, which we're going to see in just a second is going to be an issue. Let me make this a lot smaller. So we got a lot more than just 2, right? You have to remember that's because every time recurfib is called, the decorator is called. So we're not just seeing how long it took to call the main recurfib, we're seeing how long it took to call this recurfib and both the ones that it called and both the ones that one called and so on and so forth. So there's all of these. So maybe you could use this to count the number of recursions or something if you wanted. But that's not what we're interested in. We're interested in seeing how long it's going to take the entire function to run. We don't want to have to sort through all this. So I'm going to take the decorator off of this one and just make a little helper function, or yeah, a little helper function. And we'll call this like call recurfib. And you really only have to do this if the function's recursive. And all it's going to do is return recurfib. But this one only gets called once. So do you see the difference? This only gets called once. So the time starts at the beginning and then it ends once the this return is over, right? Whereas this one, it kept doing, it got called multiple times, as is the nature of recursion, so there were multiple timings. So there we go. Why do we only get one? Oh, we need to do call recurfib down here. All right, there we go. So there's both of them. And let's get this back up to something rather large so we can see the difference. Okay. Alrighty, so that's a decorator in its most basic sense. Remember, it's just a function that takes a function as an argument creates a nested function, then returns that nested function. And you can add operations before and after the function inside because you got to call it. So, all right, let's see what we can do with this. Let's make another function because we want our decorations to be able to work on anything, right? If you take your Christmas lights or your Halloween pumpkins down to the next house on the street, you want them to still be applied in the same way. Your decoration should not be house specific. That's not going to be good. So let's just make another function. This one's not even going to be, it doesn't have to be anything similar to Fibonacci. Let's say sum two arrays. And it's going to take an array A and an array B. So do you want to do this the hard way or the easy way? And let's just do it the trivial way. There's better ways. You could use Python's sum method. You could combine the arrays, but let's just do it like this. So for element in A, we're going to assume that these are arrays of like integers or something, or strings, something that can be concatenated or added together. S plus equals element, or element in B, S plus equals element, return S. And yes, like I said, I know there's many better ways to do this, or slicker or cooler ways to do this, but let's just keep it readable for now because we're not interested in solving this problem the best way possible. Alrighty, so now we need an A and a B. Let me import random. There's no better way to get a random list, at least not easily. Random.random. There's no 1 in 100 for X and range. Actually, we're not even using the X. So in Python, if you're not going to use the variable you're iterating over, you can just use the little underscore. Let's just put 100 items in there, 1,000. And that's a list comprehension if you've never seen one before. I'm not going to explain how it works here. I've gone into too much detail on other things. I might make another video in the future explaining exactly how to translate a for loop into a list comprehension, but just know that these are going to be arrays of 1,000 integers each. And I'm not going to print them because they're going to be too big. So the sum is going to equal the sum of two arrays, A and B. I will print the sum. All right, so we just wrote a lot of code. Let's see if we got everything right. And we did. Okay, cool. So there's the sum. Cool. So the first thing we might want to do is get rid of this Fibonacci specific stuff here in the print statement. Let's just print the time that it takes to execute. All right. Cool. And then it'll be up to the caller to do something with the return because the Fibonacci number is this F here, so we still have it. And let's decorate our sum of two arrays. Let's figure out how long it takes to do that. Uh-oh, we got an error. So the sum of two arrays was the function that was passed into time. So F is sum of two arrays. Then we try to call it right here. We give it N. So effectively we gave it like, well, we got an error, right? We didn't even give it A. It doesn't take one argument. It's not like these Fibonacci's. Fibonacci takes one element or one parameter, and it's a required parameter. It's not a keyword argument. Whereas the sum of two arrays needs two. How can we reconcile that? How can we somehow get our inner function to work no matter how many parameters are getting passed? Well, remember, we looked at earlier, the print function can take any number of arguments, any number of parameters. You can just keep going like this all day long, as long as you keep putting commas between things. That's the sort of functionality that we want to use. How does the print function do that? If you've never considered it before, it's a pretty big question. It stares you right in the face, but you've probably never written a function that was able to take infinitely many arguments. So let's actually peel back the curtain and see how this works. So this inner function is going to take something called args. And the interesting and kind of weird thing is you have to put this asterisk, this little star in front of it that unpacks the arguments. So it's sort of like there's a tuple of them and you've unpacked them. So let's say you got args is 1, 2, 3, 4, 5. If you were to do this, I guess you can't do that there. Anyway, it unpacks it into the different pieces. That's sort of the idea. So, okay, now we can take as many arguments as possible. And then we just put the args in there. So we just kind of pass them along. But this isn't a fib anymore. Now it's more like the return. So whatever it returns, return it there. Ooh, so look at that. We got the sum and we got the time that it took to execute the sum. So that worked. That's pretty cool. Let's look at one more example. Let's see. What would be a good function for this? Something really simple. We're going to print greeting. So hello is going to equal hello world by default. So I'm sure you've seen that sort of thing before. And if not, go back to your intro class and think about what these keyword arguments are. So we're saying, hey, this one's optional. And we're going to save it to a variable called hello. And if they don't give us one, it's called hello world. So how might you use it? Print greeting, sup. Print greeting with nothing. So we get sup and we got hello world. So let's apply our time it to that function. So we got hello world, then we got, let's see, it printed sup. There's the time to execute, hello world, time to execute. All right, cool. So I guess that worked just fine. Anyway, best practice is up here. You want to use keyword args. And this might come into play if we had a more complicated function, something that had more going on. But using the double star and then by convention, KW, keyword args, grabs all of these things and unpacks them so that you can pass them into your function as well. I wonder if we did something like this, if we can maybe mess it up. Well, we can't mess it up now because we changed it up here. Okay, anyway, so this is the basic template for a decorator. You're gonna have your name of the decorator, whatever your decoration is. It's gonna take a function as an argument, call it f, call it func, call it whatever you want. Well, not anything you want, make sure it's at least a little bit descriptive. And inside of it, it's basically gonna have a factory. So here is the function, behaving just as normal, passing in whatever arguments it had. So this will work on any function now. Any function with any arguments. 0 arguments, 100 arguments, 10 arguments, doesn't matter. It'll work on it. And then you got to make sure that it returns the value that this function returned. So you can still use it the same way, but just with the added functionality of being able to time, in this case, to time how long it took the function to work. So you could do multiple other things with this, but I'll leave that as an exercise for you. But whenever you have multiple functions and you want to do something to them, maybe you always want to do something before, you always want to do something after, you want to use this decorator pattern so that you can just come along and add these decorations to your function calls. All right, so hopefully this made sense, and I think we'll end the video here. So this has just been a brief overview of how to use decorators in Python. All right, see you in the next video.